The lattice energy is the energy that is required to essentially rip apart an ionic compound. Let's say, for example, that we had some calcium chloride, CaCl2. That's the formula for that ionic compound. And that we wanted to rip apart this calcium chloride. So I'm going to draw a chemical reaction arrow. We are tearing this ionic compound apart. So that means that we're going to be taking those calcium ions, which are Ca2+, and we are going to be pulling them completely away from the chloride ions. We've got 2 chloride ions in this compound. I know that because I've got the 2 here. 2 chloride ions. We're basically pulling all 3, 1, 2, 3 of these ions away from each other. If we wanted to do that, how much energy would it take to actually pull these molecules apart? That energy is called the lattice energy. Now, if you're looking for a video on how to calculate lattice energy, you've come to the wrong place. We're not going to do any lattice energy calculations at all. We're just going to do some qualitative, non-mathematical predictions about lattice energy. The lattice energy is actually a little bit more complex than what I've described and written here. So the definition of lattice energy is that it is the energy that is required to convert 1 mole, so we're talking about a very specific quantity, 1 mole of a solid ionic compound. So not all ionic compounds, they're not always in the solid state, but the lattice energy always involves starting them out in the solid state, not a liquid state, not a gas state, converting 1 mole of a solid ionic compound to ions, so we know what that is, in the gas state or the gas phase. So not only are we ripping these ions apart, but we're also vaporizing them, turning them into gas. So you can imagine there's quite a bit of energy going on here. The lattice energy of an ionic compound is based off of 2 things. It is based on the charge of the ions, and it's also based on the size. And in this video, we're just going to talk about how charge and size affects the lattice energy. First of all, with regard to charge, the greater the charge is on an ion, and it doesn't matter if it is positive or negative, just the higher the charge, the stronger the lattice energy is. I'm going to abbreviate it LE. And this should make sense to you because if we have a high charge ion like a +2 or a -2 or even a +3, -3, that indicates a very powerful positive charge or a very powerful negative charge, which means that those ions are going to be held together with quite a bit of force. It's like a strong magnet, and that means it's going to take more energy to pull those apart. So say if we were comparing CaCl2, which we have up above, versus something like KCl. In the CaCl2 compound, we have calcium ions with a +2 charge, chlorine ions with a -1 charge. In KCl, we have potassium ions with a +1 charge, and then chlorine with a -1 charge. The +2 charged ions of calcium, because they have a higher charge, that means that the CaCl2 will have a higher lattice energy than KCl, which will have a lower lattice energy. So in just comparing just these 2 right here, we can say that calcium chloride will have a higher lattice energy, which just simply means that it'll be harder to pull those ions apart from each other. Now our second factor here is the size of the ions that are in the compound. The smaller the ion is, the higher the lattice energy will be. Now this one is not quite as intuitive as the charge, but if we have, let's try to draw some pictures here. Actually, let's first write some formulas. So let's say we have NaF versus NaCl. So we have a sodium atom, let's say it's this big, and a fluorine atom, let's say it's this big. Got kind of a weirdly placed nucleus there. Sodium atom and a fluoride atom like this. And then over here we have a sodium atom. I'm going to try to make my two sodiums the same size. And chlorine, the chloride ion is larger than the fluoride ion. So chloride like this, maybe bigger. I want to make it bigger. And so what we see, what we know is that these two ions are held together with more energy, a smaller ion, higher lattice energy. So these two ions are held together more tightly than these two ions. And we know it has something to do with size. And so what we know is that because the chloride ion is so big, the nucleus of the chloride ion is actually pretty far away from the electrons of the sodium ion, whereas the nucleus of the fluoride ion, because it's smaller, they're actually able to come closer to the electrons of the sodium. So the smaller size helps these two nuclei get closer together, and that helps hold the ions together with a greater force. So because this is smaller and the chlorine is larger, we know that the NaF will have the higher lattice energy and the sodium chloride will have the lower lattice energy of the two.